Hi, Algebra 2 honor students. This is going to be Unit 16, Day 4. Today we're going to learn some new identities to add to the list. So if you have a separate sheet going with all the identities on them, add a few more to the list today with what are called the sum and difference identities. And as a quick caution, it seems like this has the potential to be true, that sine of x plus y would equal sine x plus sine y, but sine is not a distributive function. Okay, so if this was like some scalar number, the distributive property would work, right? If this was a 3, you can distribute a 3 in. But sine in it of itself is not a number, it's a function, and it doesn't distribute across the x and the y. So sine of x plus y does have a formula, and I'm going to write down sine of x plus or minus y right now. So if it's the sum or the difference of two angles, here's what sine of x plus or minus y would equal. It would be sine x cosine y, and then cosine x sine y. And what I'm going to do in the middle here is write down the signs that are associated with those sum and difference. So sine, the sign in the middle stays the same. And that's going to be a way that we remember that. For sine of a sum, it's going to be a sum here. For sine of the difference, it's going to be the difference in the middle. Okay, so that's sine of the sum of two angles, and we'll see why we need to apply these in certain examples today. Cosine of x plus or minus y would be the following. It's going to be cosine x cosine y, and then over here, sine x sine y. Now for cosine, what we'll notice is that the sign in the middle changes, so it's going to be minus over plus. So if it's cosine of a sum, this becomes a difference. Cosine of the difference, this becomes a sum. And for cosine, we have a change of sign. So that's a quick way to remember that, change of sign. And then finally for tan of x plus or minus y is going to be a fraction. So the way we represent tan of the sum or difference is going to be tan x, tan y. I'll show you the signs on top there in a second. And then 1 tan x times tan y on the bottom. And what we're going to wind up having here is it's tan of x plus or minus tan of y on top. The bottom, it switches to minus over plus. So if it's tan of the sum, it's sum up top, difference on the bottom. If it's tan of the difference, keep the difference on the top, and then change it on the bottom. Now, the great thing about these is if you're like, oh man, I missed one tan as a secret, and signs cost $1, and all those little tricks. These we actually chant. So I'm going to do this with you a lot in class, but for sine, it's going to be sine, cosine, cosine, sine. That's the pattern, sine, cosine, cosine, sine. For cosine, it's cosine, cosine, sine, sine. And you're going to repeat after me, so get ready for it, because it's coming. For tan, the pattern is tan, tan, 1 tan, tan. Right? So it's sine, cosine, cosine, sine, cosine, cosine, sine, sine, tan, tan, 1 tan, tan. And it goes that fast once you know the patterns as thoroughly as I know them. So why do we need these sum and difference identities? Because we're going to use them to find the exact value of things that are maybe not such special triangles. So find the exact value of the following. Number 1, let's figure out what's cosine of 15 degrees. So to do cosine of 15 degrees, there's no special triangle I can think of that has a 15-degree reference angle, right? I don't know how to label those sides. However, we can express cosine as either the sum or the difference of two angles that are special. What are some of the special angles that we know? Well, like 30, 45, 60, those are all special angles. So can I think of how I can use these special angles to get 15 degrees? And the answer is sure. We can actually do a few different things. The easiest choice might be to do 45 minus 30. 45 minus 30 certainly is 15. Now, when I go to evaluate here, I'm not going to fall into this trap of the caution up here. I can't just distribute cosine. Cosine of the difference of two angles is cosine, cosine, sine, sine. So let's go ahead and write that out. It's going to be cosine, cosine, cos 45, cos 30. For cosine, there's a change of sign in the middle, so plus sine 45, sine 30. Okay. Now, what I'm going to do is evaluate each and every single one of these, and then in the end, be able to sub back in and simplify the fractions that we're getting. All right, so for 45 degrees, I can draw a quick reference triangle if I need to. The sides are 1, 1, radical 2. Similarly, for 30 degrees, we can draw the reference triangle with 1, radical 3, and 2. I'm going to do that part of it pretty quickly, so If you need a second to kind of catch up, that's fine. Cos 45 adjacent over hypotenuse would be 1 over radical 2. I'm going to rationalize it right away because we do tend to write simplest radical form answers. Cos 30 adjacent over hypotenuse would be radical 3 over 2 from this triangle, plus sine 45 would be radical 2 over 2, just like cos 45. Sine 30 is a half. From there, if you multiply these pairs, this is going to give you radical 6 over 4 plus, this is going to be radical 2 over 4. And the exact value, no decimals, anything like that, for cosine of 15 degrees is radical 6 plus radical 2 over 4. Please don't try and make that radical 8. You can't add unlike radicals. This is as simple as we can get it for cosine of 15 degrees. Okay. So what if I said, well, let's try something like sine of 105 degrees. Could we do sine of 105? I think we could. We have to think about two angles that either add or subtract to 105. And again, you might have a few options there. But why not try something like sine of 60 plus 45? 60 and 45 certainly add up to 105. Those are special reference angles. So for sine, it's going to be, if I use my identity, sine, cosine, cosine, sine. Okay, so it's going to be sine 60 cosine 45 plus cosine 60 sine 45. And then we're just going to plug those ratios in just like I did up here a minute ago and get those exact values. Now, I'm going to try and use these same two triangles so I don't have to redraw them again, keeping in mind 60 is right up here. So we can easily do sine and cosine of 60 if needed based on that same triangle for 30. So sine 60, opposite over hypotenuse, would be radical 3 over 2. Cos 45, we already did a second ago. Cos 60 is a half. Sine 45, radical 2 over 2. So this becomes radical 6 over 4, plus multiply those to get radical 2 over 4 for a final answer of radical 6 plus radical 2 over 4. Strange. Why am I saying strange? That looks pretty much identical to the answer up there. There must be some sort of special connection with cosine and sine going on there. Okay. So we can talk about that in class. I might be asking you, what is that special connection that I'm referencing? Let's try something with tan, just so we can see what that formula looks like. Tan might be one of my favorite ones to chan. I don't know. It might be personal preference on my end, but something like tan 75. Again, thinking about some special angles that combine to 75. Let's go like 45 and 30. That seems like those will nicely add up to 75. The formula for tan is tan, tan, 1 tan, tan. So using that pattern, it's going to be tan 45 plus tan 30 over 1 minus tan tan, the product of those two. Okay. So if you need those reference triangles again, you can use them. Okay, you can go back to this page. We have 45, we have 30 right there. So let's go ahead and plug in what we know. Tan 45 is just going to be 1. It's 1 over 1. Plus tan of 30. Tan of 30 is 1 over radical 3. If you look at the triangle, I'm going to rationalize that right away to radical 3 over 3. The bottom's going to be 1 minus the product, 1 times radical, or 1 over radical 3, which is radical 3 over 3. Okay. So cleaning this up, we wind up getting 1 plus radical 3 over 3, and then 1 minus radical 3 over 3 if I multiply these together. And I'm going to show you some really quick simplification steps that are going to get me to the final answer, because now it's all about simplifying. First of all, we have a complex fraction whose LCD is 3. So we're going to multiply the top by 3, the bottom by 3. That's going to give you 3 plus radical 3 on the top and 3 minus radical 3 on the bottom. It almost seems like those sort of cancel out, but they don't. Okay, they're not the same quantity, one separated by plus, one with minus. So the last step is to multiply by the conjugate, which it's been a while since we've done this, but the conjugate is take the denominator and change it to a plus in the middle, just change that middle sign. And then multiply across the top and across the bottom. Let's see what happens. The top is going to be 3 times 3, which is 9. You're going to get 3 radical 3 and another 3 radical 3, so that's plus 6 radical 3s. Plus radical 3 times radical 3 is 3. I'm doing that pretty quickly there. Double check it with box method or whatever you need to. Conjugate pairs, you just have to do the first product minus the last. So 3 times 3 is 9. minus radical 3 times radical 3, which is 3. And cleaning this up, what happens? We get 9 plus 3 is 12 plus 6 radical 3 on top. The bottom is 9 minus 3, which is 6. And we're so close. Divide 6 into both of those to get a final answer of 2 plus radical 3. Okay. So that was a little bit algebra heavy at the end to be able to simplify, but something that we could do using some properties from earlier on with simplifying radicals. Okay. We won't see this too much, but when we do, we'll try and simplify it and get it into simplest radical form. All right, what if I gave you something that maybe already was expanded with the sum and difference formula? So if I give you cos 96 cos 6 plus sine 96 sine 6. Okay, 96 degrees and 6 degrees don't sound like special angles to me, and they shouldn't sound like special angles to you either. So I can't just like go and sub in some special ratios here and figure out what that is. But this certainly looks like a pattern of one of the sum and difference formulas for which one is it? Well, let's see. If it's cosine, cosine, sine, sine, it's going to be a cosine formula. It's important to remember, too, that with cosine, the middle sign is different from what we're actually doing with the two angles in question. So this is the angle x, and this is the angle y over here, the 6. So when I do cosine, cosine, sine, sine, this is the same thing as saying cosine of x minus y. Because remember, for cosine, that change of sign there, if it's plus, it's really the difference of two angles. What are the two angles that we're subtracting? How about 96 minus 6? And 96 minus 6 is 90 degrees. Oh, wait, now this is actually a really nice answer. Cosine of 90 degrees on the unit circle would be the x value. So cosine of 90 is 0 for a final answer. So when you see something that's already expanded out, think of which formula is it? Is it sine? Is it cos? And then kind of work backwards. Okay, squeeze it into the an identity of just cosine of a single angle, and it should be a single angle that we can easily evaluate there. Okay. All right, last but not least, let's do a quick proof. How can we do proofs with these? Well, we can show that cosine of 180 minus theta is equal to negative cosine theta. This is the last one that we'll do. Okay. All right, I'm doing cosine again, but how do we expand a cosine difference formula where this is the angle x and this is the angle y? It's going to be cosine, cosine, sine, sine. So cosine 180, cosine theta. Cosine, there's that change of sign, so it's plus in the middle now. Sine 180, sine theta. Okay. So in the end, I want to show that this somehow equals negative cosine theta. And notice how there's two things we can evaluate here, because these are specific angles. We have cos 180 and we have sine 180. So I'm going to draw my unit circle over here just to remind me of those values. If we're at 180, which is the point negative 1, 0, cosine of 180 would be the x value, so that's negative 1 times cos theta. Sine 180 is the y value, so that would be 0 times sine theta. Well, 0 times sine theta is 0. Negative 1 times cos theta is just negative cos theta, which happens to be exactly what we have on the other side. So within an identity proof here with the sum and difference identities, something like this wouldn't take us very long to prove that it's true, but it is going to rely on some of our unit circle knowledge. Okay, so that was a really quick intro into sum and difference. We're going to do another day of practice with sum and difference. So if this was a little too fast for you, we've definitely got more practice to come. Have a great rest of your day.